Thanks so much, Neil. So yes, thanks everyone for coming, and thanks to Neil and Joe for putting the conference together. I've really enjoyed all of the talks so far and feel I've learned a lot from them. I've kind of been lurking in the background as I've been simultaneously trying to look after a newborn, but he's also learning a lot about alternative approaches to scientific realism. Okay, so what am I going to be talking about today? The idea is this. So contemporary physics presents us with a range of more or less recherche objects. And I think it's incumbent on us as philosophers to try and make sense of them. And I'm going to argue that in order to make sense of some of these objects, we're going to need to go to some kind of perspectival realism. So in more detail, here are the points which I'll be covering today. So contemporary physics, populated with a range of fantastic beasts, pseudotensors, tensor densities, spinors, and so on. Philosophers of physics have focused their metaphysical considerations on only the most prosaic of these for the most part. For example, tensors. So people will look at the Faraday tensor representing electric and magnetic fields, for example. But we should be thinking about the metaphysical status of all of these objects. And as I said, I'm going to be arguing that when it comes to some of these, in particular, I'm going to be looking at pseudotensors. If we want to make physical sense of them, one way to do it would be to be a perspectival realist. So here's the plan. I'm going to start off by just reminding you about some details about natural kinds and projectable predicates. This is all very standard stuff, so I'm only going to spend a slide on it. It will be familiar to almost everyone already, I think. I'm then going to spend much more time talking about the notion of a geometric object, which is a technical term from the 20th century. And I'm going to argue that there's a case to be made that geometrical objects can be assimilated to natural kinds, but non-geometric objects, including pseudotensors, cannot. But we're also going to see that there might be some grounds for questioning this way of carving things up. So for example, Brian Pitts, who I think is with us today, would want to identify some non-geometric objects as natural kinds as well. So we'll see how those arguments go. In the third part of the talk, I'll then connect this up with the terminology from Ladyman and Ross. So drawing on the kind of division from the previous section, you might think that there's a case to be made that geometric objects can be associated with real patterns, but non-geometric objects can only be associated with what Ladyman and Ross call mere patterns. But again, one might question this. So I think there's a bit of a tension between what Ladyman and Ross say and what Pitt says here, which I think will be interesting to look into. In the next section, I'll then connect this up with perspectivalism and this other thesis, fragmentalism, which is due to Fine, and there's an interesting recent paper by Lippmann on this idea as well. I'm going to be seeing how perspectivalism and fragmentalism might provide us with some way of understanding the physical content of pseudotensors. But I'm also going to be arguing that perspectivalism is to be preferred over fragmentalism. Then in the last two parts of the talk, I will think about how these kinds of views connect up with some other in vogue points of discussion in the contemporary philosophy of physics and philosophy of science literature. So I'll see how this perspectivalism interacts with the dynamical approach to spacetime, currently very popular in Oxford. And then in the last part of the talk, I'll think about how these things connect up with Neil's sophistication about symmetries. Okay, so let's start. Natural kinds and projectable predicates. So what is projectability? I'll just use Blackburn's definition. So it's a property of predicates measuring the degree to which past instances can be taken to be guides to future ones. What's a natural kind predicate? Well, these are supposed to be associated with joint carving properties, properties which reflect the objective structure of the world in some sense. And you might ask, what's the connection between a natural kind predicate and a projectable predicate? In his 1969 paper on this, Quine said that a necessary condition for being a natural kind predicate is projectability. It better be the case that I can continue to use these predicates in the future if they're going to be associated with natural kinds. But note that projectability isn't necessarily sufficient for being a natural kind predicate. So for example, is green or blue is a perfectly projectable predicate, but no one thinks that green or blue is a natural kind. So just to give an example, everything in the jewelry shop is gold or silver. So everything in the jewelry shop in a week's time will be gold and silver. Gold or silver seems fine as a projection of that predicate, but no one thinks that gold or silver is a natural kind. Okay, now let's move on to geometric objects. So this is a formal concept, which goes back at least to Nijenhuis and Schouten in the 1950s, and which was later developed by Troutman. And here's the idea. So For a differentiable manifold, consider an arbitrary point in the manifold and two local coordinate systems around that point. In order to specify a geometric object on that manifold, you write down a set of components, which is a set of n real numbers in each such coordinate system, and a well-defined rule relating the components in one coordinate system to the components in the other. If the second is lacking, then Nijenhuis dubs the resulting entity a mere object. If you just got the components, but you don't have a well-defined transformation rule between them, it's a mere object. I'll call anything which isn't a geometric object a non-geometric object. So what's this idea of a well-defined transformation rule? The idea is that your transformations have to be transitive in a certain sense. So if you start off with the components of your object in one coordinate system, and then you transform those to the components in some other coordinate system. So start off with some coordinate system A, transform to some coordinate system C. That's got to yield the same result as transforming via some intermediate coordinate system B. So if I transform from A to B and then B to C, I should get the same thing as if I transform from A to C. And this is going to be violated in a quite famous case, in the case of spinors, where if you do nothing, you won't pick up a minus sign. If you rotate by 2 pi, by like rotating by pi and then pi by again, you'll start picking up minus signs. So spinors are not geometric objects. If you want to know more about what constitutes a well-defined transformation rule, I'd recommend this recent paper by Patrick Durr, which goes into it in a lot of detail. Okay, so here's a list of geometric and non-geometric objects then. So geometric objects include tensors, tensor densities, where your transformation rules pick up factors of a Jacobian as well. Christoffel symbols, which don't transform like tensors, they pick up extra terms, but they still have well-defined transformation rules. On the other hand, non-geometric objects include pseudotensors, spinors, and other objects besides. In most of the examples, which I'm going to be looking at in today's talk, I'll think about pseudotensors, but I think a lot of what I say will apply to lots of different kinds of non-geometric objects. Okay, so let's think about pseudotensors in a bit more detail. I'm also, like Noah, going to be talking about gravitational or stress energy conservation laws in general relativity, so interesting connections there. So perhaps the most famous non-geometric objects are the gravitational stress energy pseudotensors, which appear in general relativistic energy conservation laws, which take this form. So this says that the divergence of the sum of the material stress energy content and the gravitational stress energy content should vanish. And Einstein wrote down things like this, and they formed a lot of discussion in the 1910s, and that discussion hasn't really stopped since. A lot of people feel quite queasy about these conservation rules for a lot of different reasons. So here are 3 reasons why some people don't like them. The first is that in general relativity, there are in fact infinitely many such conservation laws, one for each rigid symmetry of the Lagrangian. The second is that such conservation laws are closely related to mathematical identities, which somehow people think must mean that their physical content is diminished. And the third, and the one that I'm going to focus on today, is that the pseudotensors representing gravitational stress energy, which feature in these conservation laws, are not geometric objects. They don't have well-defined associated transformation rules. So there's a lot to be said about these first 2 as well. Just in brief, with Pitts, who has a great 2010 paper on this, I think that one should just trust the mathematics. If you get infinitely many conservation laws, then you have infinitely many conserved quantities in general relativity. In the second, I think that the connection between a mathematical identity and physical content is at least non-trivial. And it's not obvious to me that identities can't have physical content. But I will bracket both of these and focus just on the third one. So we've got these gravitational stress energy pseudotensors. They don't have well-defined transformation rules. This is forming part of the argument against the legitimacy of gravitational stress energy and overall stress energy conservation in general relativity. But we want to dig down into what exactly is supposed to be problematic about these non-geometrical objects. So it's sometimes simply asserted that geometrical objects are the sine qua non of reasoning in contemporary physics. It's not really an argument against non-geometric objects. So what's wrong with them? Well, one possible reconstruction here is that there's something dodgy about their lack of transformation rules. in a certain sense, which I think is not the same sense of projectability that we were talking about in the previous section, although I think it's ultimately related, these objects are non-projectable. You can't transform their components in one frame to their coordinates in another frame, making them somehow pathological or ethereal in a way that geometric objects aren't. So we would like to understand this in more detail now. So now I have to connect up with something that Noah was saying in the intertalk discussion period, Klein's Erlangen program, his approach, Kleinian approach to geometry. So on this approach to geometry, you can identify geometrical structures by way of specifying a set of transformation rules and considering the invariants of those transformations. The objects so identified will coincide with those specified in a coordinate independent manner on another approach to geometry, the so-called Riemannian approach to geometry, which is popular in certain places in the philosophy of physics, so Chicago and Irvine and so on. This is actually not an entirely obvious claim, and it's not completely obvious that this can always be done. So it's not always obvious, well, it's not at all obvious that you have, or we have a coordinate independent description of tensor densities. This is a point which Brian Pitts made to me last week when we were chatting about this material. But I'll set this aside. Maybe optimistically, someone will come up with a coordinate independent characterization of densities in the future. I'm just going to kind of take this for granted in the remainder of this talk. So the thought then would be that you can associate geometric objects as defined above with objects specified in a coordinate independent manner. Not so for geometric objects. And Pitts uses the terminology of natural kinds here. He writes, thus the components of a geometric object form a natural kind mathematically. They constitute faces of one and the same entity by virtue of being interrelated by a coordinate transformation rule. Interestingly, Quine also says something about this very briefly at the end of his natural kinds paper. He also alludes to the connection between natural kinds and Klein's approach to geometry. He writes this: perhaps the branches of science could be revealingly classified by looking to the relative similarity notion that is appropriate to each. Such a plan is reminiscent of Felix Klein's so-called Erlanger program in geometry, which involved characterizing the various branches of geometry by what transformations were immaterial to each. So there's a connection here between something having well-defined transformation rules, our ability to construct an invariant object, and those invariant objects being associated with natural kinds. In sum then, or just to summarize a bit, the fact that geometric objects have well-defined transformation rules makes them, in a certain sense, projectable, and thereby candidates of being associated with natural kinds, not so for non-geometric objects. And that's bolstered insofar as these transformation rules allow for the identification of invariant entities via the Kleinian approach. The fact that you can't do this for non-geometric objects which don't have these transformation rules might lead one to doubt whether they can be associated with natural kinds. So there are some follow-on questions here. The first would be, are all geometric objects to be assimilated to natural kinds or only a subset? And if the latter, how to identify this subset? And the second would be, is it actually true that non-geometric objects are not to be assimilated to natural kinds? Or are there arguments to the contrary? So on the first, I think the situation is kind of like the green or blue predicate from before. You've got some geometric objects which we think are more joint carving than others. Maybe the metric tensor is more joint carving than the Schouten tensor or some other random contraction of indices. I'll say a bit more about that in a second. On the second question of whether non-geometric objects can ever be associated or assimilated to natural kinds, I think both positive and negative answers are available. So the negative answer would look something like this. This isn't a quote of anyone, it's just something that someone might say. The thought would be this: in light of the lack of transformation rules between the components of such objects in different coordinate systems, there's no unified coordinate independent entity to be associated with such objects. In this sense, non-geometric objects don't adequately limn reality. I think that's a fair line of thought, but let's also think about the positive response, which would look something like this. Non-geometric objects can still limn the elements of reality. It's simply that these elements can't be represented in a non-perspectival manner, i.e. without reference to a coordinate system. And in this 2010 paper from Pitts, he seems to write something along these lines. Pitts says, a pseudotensor shares with the Einstein tensor the physically interesting property of having a single recipe for inferring its components in a coordinate system from the metric components and their partial derivatives in that coordinate system. Thus, the components do form a natural kind in that physical sense. However, there is no transformation rule that allows one to infer the components with respect to one coordinate system from the components in another. So there's no mathematical unity. So Pitts is thinking that the lack of transformation rules doesn't necessarily impinge upon the status of this object as a natural kind, some joint carving element of reality. And I think the thing to think about is Pitts really being so unreasonable here? You might think that there are many criteria for something to qualify as a natural kind, of which having well-defined transformation rules is only one. If gravitational stress energy pseudotensors, say, met a bunch of other desiderata on energy, they seem to share lots of analogies with other energies in other theories. One might ask, might not that be sufficient for it to qualify as a natural kind in the case of general relativity as well? I think ultimately what's lacking here are clear and well-articulated criteria for an entity to be associated with a natural kind. Usually people just say the lack of transformation rules is completely damning for non-geometrical objects, but I think that's much too fast. We need to weigh these kind of positive considerations against these kind of negative considerations. And maybe we do want to introduce objects which are kind of multi-perspectival, but they don't admit of any independent, coordinate independent representation. Okay, so now let me connect up with the terminology which Ladyman and Ross use. So I think James Ladyman's here, so he can correct me if I say anything wrong about their picture, but I take it to be something like this. So the ontic structure realist ontology is cashed out in terms of real patterns, patterns in our description of the world, which are both projectable and maximally information compressing. And they write, we contend that everything a naturalist could legitimately want from the concept of a natural kind can be had simply by reference to real patterns. So if I'm to bring this into contact with the stuff that I've already said, we might say that being a geometric object is sufficient for projectability, at least in the sense of having well-defined transformation rules. And a certain subset of these will satisfy the maximal information compressing criterion. So maybe the metric tensor does, but as I said, some random contraction of indices might not. But Ladyman and Ross also go on to talk about mere patterns. And they say a mere pattern is a locatable address associated with no projectable or non-redundant object. The idea here is that given the structure of the world, you can lay down further structure, what they call locators, in order to identify salient aspects of that structure. And it's via that process that typical metaphysical notions of objects and properties and events and processes arise. But what's identified relative to such a locator can't exist in anything but an ontologically thin sense. The true structure of the world remains the structure described directly by the physical theory or scientific theory under consideration, without the aid of a locator. So one example of a locator is a coordinate system. So for Ladyman and Ross, a structure defined relative to a coordinate system could be at best a mere pattern. But now we can bring this into contact with our previous discussion of pseudotensors. So non-geometric objects such as pseudotensors can indeed be characterized only relative to coordinate systems. So it seems that what one should say about those kinds of objects in the language of Ladyman and Ross is that they're not to be taken ontologically seriously because they're not projectable and not natural kinds, are mere patterns. Here's the tension which I alluded to right at the start of the talk between what Ladyman and Ross say and what Pitts says. I think Pitts is going to say, you might still want to regard these as being real patterns, as being natural kinds, because they satisfy a bunch of other desiderata. So we've got this disagreement between the two, and I'm not exactly sure how to resolve it, but I just want to point to it. Okay, so now enters perspectivalism. Even granting that non-geometric objects are associated only with mere patterns, you might ask, is there any sense in which you can regard them as being physical or having physical content? And I think potentially yes. So what is a space-time coordinate system? You can think about it, if you want, as kind of an idealized vantage point of some observer. What's described using a such a locator, such a coordinate system has the capacity to be amenable to empirical access. So you could lay down a coordinate system where you imagine your idealized observer is at the origin, and then you can talk about stuff being like 5 meters away from that observer or whatever. So an alternative take on such non-geometric objects, such mere patterns defined only relative to coordinate systems, is that they're real but perspectival. Your pseudotensors, say, admit of many different perspectival descriptions, but they don't admit of an invariant description. So embracing the reality of the objects represented by, say, two pseudotensors, and also of the space-time coordinate representations of geometric objects, is one form of perspectival realism. And I think you kind of need this if you're going to make physical sense, if you want to make physical sense of non-geometric objects like pseudotensors. So some of these issues have been discussed under a different name in recent literature, under the guise fragmentalism, which is a term coined by Kit Fine in 2005. So Martin Lippmann has a nice paper in Philosophical Studies from last year where he talks about this in the context of special relativity. And he basically says that the fragmentalist is committed to the existence of not only invariant facts, the existence of a Minkowski metric field in special relativity, but also frame relative facts like this particular time dilation of this clock or this particular length of a rod in a particular frame. Here's how Lippmann puts the view. The importance is that of marking a metaphysical realism about those variant matters. The relevant question is whether realism or anti-realism is true about the frame relative facts. That is, whether consideration of the special theory of relativity removes all frame relative facts from one's metaphysical conception of reality. The Minkowskian, i.e. kind of invariantist, answers yes. The fragmentalist answers no. I think this is fine, but there's much to commend in Lippmann's paper, but it's a bit ambiguous between perspectivalism and fragmentalism, and I kind of want to tease these out. So let's start off with perspectivalism. So this involves a commitment to the reality of frame relative facts. So just to F, but doesn't have that property in some other frame G. Then using Freine's reality operator from his paper, which is meant to denote one's realist commitments, you might, as a perspectivalist, assent to the reality both of A having P in F and A not having P in G. These subscripts illustrate or indicate the frames that we're talking about and whether A has that property in one frame or another frame. Here, the overall set of realist commitments isn't self-contradictory. These two commitments are not contradictory. But what Fine and Lippmann say is that almost the defining feature of fragmentalism is that the overall collection of facts, uber reality, includes pairs of mutually incompatible facts. So if we say what we said on the previous slide, that can't be fragmentalism. I think one way to understand it is just that the fragmentalist ditches the subscripts. So they assent both to A being P and A not being P, i.e. a genuinely self-contradictory set of realist commitments. At this point, I get kind of puzzled. I think in actually a genuine sense that I could explain in the Q&A if people want, it's too Hegelian for me. So I'm only going to assent to perspectivalism in the remainder of the talk. That perspectivalist position does, however, seem to address concerns about how you can be realist about gravitational energy while abandoning the paradigm that only geometric objects have physical content. Because you believe in, the gravitational stress energy in such and such a frame is this quantity, the gravitational stress energy in such and such a frame is this quantity. You just don't have a well-defined way of transforming between them. Since there's no coordinate independent representation of the entities under consideration in the case of non-geometric objects, arguably these afford a better motivation for perspectivalism or fragmentalism than talking about the frame relative effects and special relativity. Because in the case of special relativity, you actually do have an invariant description with respect to Minkowski spacetime available, but you necessarily don't have that when you're talking about gravitational stress energy in general relativity. So they kind of force your hand towards something like this view, whereas your hand isn't so forced in the context of SR. Okay, so there's a critique of fragmentalism, again, thinking in the context of special relativity, which was raised against the view by Hofweber and Lang in a paper from Noose a couple of years ago. Here's Lippmann's summary of the critique. I don't think it works. So the summary is this. So the fragmentalist interpretation under discussion, which takes the variant properties to be real and the grounds for the spacetime interval, cannot offer the standard explanation. The standard interpretation underwrites the standardly assumed explanatory priority of the spacetime interval, whereas the fragmentalist conflicts with it. So the thought here is, standardly we assume that it's invariant facts to do with Minkowski spacetime which can explain why we see certain frame relative perspectival phenomena. The explanatory arrow runs that way rather than the other way. Here are two responses to Hofweber and Lang. One is, why assume that this standard interpretation is correct when there are alternative approaches? So for example, the dynamical approach to spacetime of Brown and Pooley starts off with your dynamical symmetries, your frame relative descriptions, and attempts to ground invariant spacetime structure in terms of those frame relative descriptions rather than the other way around. So in that sense, it seems like Hofweber and Lang are just kind of begging the question because they're setting aside these views. Also, even being an invariantist, I don't see anything wrong with the following combination of views in special relativity. The form of the coordinate transformations relating inertial frames of reference is grounded in, explained by invariant spacetime structure, but nevertheless frame-dependent phenomena should be regarded as being real. That would still be sufficient to count as a perspectivalist or a fragmentalist. And Lippmann actually says things in the same vein in his paper here as well. I think maybe even more importantly, the Hofweber-Lang critique is just not going to get off the ground in our cases of non-geometrical objects where you just don't have that invariant description. No one thinks that the standard explanatory arrow runs from the invariant stuff to the variant stuff because there is necessarily no invariant stuff. Okay, I alluded to the dynamical approach. You might think or wonder how nicely this sits with this perspectivalism, which I've been talking about. So I'll have a few slides on this, and then I'll have a few slides on how this perspectivalism interacts with Neil's work. So you might think that the dynamical approach to spacetime and perspectivalism are natural bedfellows in the sense that the former begins with coordinate-dependent descriptions of the relevant physics, as I already said, and seeks to construct the associated spacetime or more generally invariant structures therefrom. You can kind of view the dynamical approach, it's all very controversial, but I think for the purposes of today, you can kind of view it as the Kleinian approach plus a kind of metaphysical gloss on the Kleinian approach. And by the way, that's the kind of thing which David Wallace says in his paper, I think from, well, it's from the special issue of Studies on the work of Harvey Brown from a few years ago. So although that's roughly correct, I think the situation here is a bit delicate. So one thing which Brown stresses, which is a point owed to Bell, is that it's possible to teach special relativity just from a single frame of reference. So just to remind you, Bell considers a classical model of an electron, and after implementing an active boost, he finds that the electron will be Lorentz contracted. It would be perfectly acceptable for proponents of the dynamical view to take the Poincaré invariant laws of special relativity to codify those physical effects observed within a single frame, and in turn to take spatiotemporal structure to be a codification of those, the symmetries of the laws. On that understanding, there's never any need for a proponent of the dynamical view to talk about different perspectives. That being said, if they don't want to think that there's a preferred frame, then presumably they should think that all frames, modulos and caveats, which I'm just about to talk about, are equally good. And so in that sense, they might be perspectivalists anyway, but they don't have to be. You could get most of the thesis of the dynamical view across just from the point of view of a single frame. There's only one limit to combining this dynamical view of Brown and Pooley with perspectivalism, which is this. So Brown subscribes to Einstein's operational understanding of coordinates, according to which you require spatial coordinates to match the lengths of rigid rods that are at rest in the coordinate system under consideration, and time coordinates to match the ticking of clocks in that system. Clearly, not all frames of reference can be operationalized in that way. So proponents of the dynamical approach who wish to subscribe to perspectivalism presumably shouldn't universally and unrestrictedly quantify over these perspectives. They should only quantify over the ones which can be appropriately operationalized. Other than that, though, I think that these two views, perspectivalism and the dynamical approach, sit relatively well together. Okay, so the last thing to say is on Neil's work. I want to think about how perspectivalism interacts with Neil's sophistication about symmetries. There's lots that I like about this, but there's a certain kind of sophistication, which Neil calls external sophistication, which I'm still a bit more hesitant about. So according to external sophistication about symmetries, if you've got some symmetry-related models of your physical theory, by treating those as if they're isomorphic, you can illuminate the theory's non-perspectival metaphysical commitments. So consider, for example, kinematically shifted models of Newtonian gravity. The thought would be, if I treat these as if they're isomorphic, I can get a handle on what the physical content of those shifted models is. And I don't need to move to the mathematically reformulated version of Newtonian mechanics set in Galilean spacetime to get a handle on the physical content of those shifted models. Just need to treat them as if they're isomorphic, and that will suffice. I don't endorse this for reasons articulated in this paper. The reason is that you have to, in my view, give an intrinsic presentation of what the non-perspectival reality is supposed to be before such declarations of equivalence are issued. And I think maybe the case of non-geometric objects raises some more concerns about external sophistication. So if you're willing, at least in principle, to countenance non-geometric objects, it's just not the case that you can always find some invariant representation of reality if you've got symmetry-related models. If you are thinking that some pseudotensors might appear, you're not going to be able to get a handle on that. So Neil in his paper appeals to the Kleinian approach. I think he's kind of implicitly thinking that pseudotensors and other non-geometric objects are never going to form part of our best physics and best understanding of the world. Okay, so let me sum up, and then I'm really looking forward to talking about this with everyone. So first of all, I've related the notions of natural kinds, projectable predicates, real patterns to the notion of geometric objects. And I've used this to provide a reconstruction of the suspicion towards non-geometric objects. That said, I've argued that non-geometric objects might nevertheless be regarded as having physical content in a perspectivalist or fragmentalist sense, but there are reasons to prefer perspectivalism over fragmentalism. I've thought about how this perspectivalism interacts with the dynamical approach to spacetime generally well, but you have to pay attention to the operational understanding of coordinates, which is implicit in this view. And I have set these views apart from external sophistication, a view about which I'm hesitant. I would want to be a perspectivalist in the sense that I've articulated today, but I'm not sure I'd want to be an external sophisticate. And I think indeed that the existence of non-geometric objects might throw a spanner in the works of external sophistication. But to repeat the intro, I hope it's not unreasonable to say that in physics, there's a diverse range of objects, not only tensors, not only scalars, but spinors, pseudotensors, pseudotensors, tensor densities, and so on. All of these deserve careful study from metaphysicians and philosophers of science. So thanks, and yeah, looking forward to the Q&A.